Hello, hello, hello. Hi, everyone. Welcome to episode 136. Very, very deep dive into eBPF with myself and James Laverack. So, as I mentioned, this is episode 136. How does eBPF actually work? And with that, I will hand over to James. Enjoy.
Hello and welcome to eCHO episode 136. How does eBPF actually work? My name is James Laverack. I'm a principal customer success architect at Cisco via the iSurveillance acquisition. I've held a number of positions in the open source Kubernetes community. I'm a former release lead for 124, and I've had a number of other positions as well. This presentation has a bunch of sample code that's all available on my GitHub here if you wanted to follow along and take a look at what we're doing as we're doing it. But I'll go through the code on the slides as well. What this talk is about how eBPF interacts with the kernel and what actually occurs when that happens. So it's really about this part. If you see a normal diagram explaining how an eBPF program loads, we're concerned primarily with this bit here. I have a little bit of assumed knowledge. Most of it is relatively rudimentary. Just some idea of what C code looks like. You don't need to be an expert, or what a pointer is, hexadecimal notation, what a syscall is, that sort of thing. You don't need to know the specifics and internals or really much about eBPF beyond it has a bytecode and it runs in the kernel. That's all you really need. Everything else I'll explain as we go along. The other thing to note is that I'm not going to be using any of the eBPF libraries. There are a bunch of these out there which help and assist with loading eBPF code, and we're going to be using absolutely none of them. The reason for that is primarily because these libraries do a lot for you, and the whole point of this talk is to explain all of the things that are really going on, which the library will obscure for you. As you're about to see, that's usually rather a good thing, but for the purpose of this talk, we won't be using them. To give a brief overview, I'm going to introduce some eBPF sample code. We're going to do some compilation, and we're going to talk about how that works. We're going to understand what the produced bytecode is and looks like, and then we're going to write a very simple userland component to interact with that kernel code. So let's start with the simplest eBPF program that we could write that does anything interesting at all. And this is it. And we're going to step through it line by line. Apart from this one, we'll talk about this first line later. The rest of it is pretty straightforward. We're going to import some stuff from the Linux kernel using its header files, in which case we're going to get imports for these two functions down here. We're going to declare a function, and the name of a function is actually somewhat irrelevant, as we'll see in a minute. We're going to get a PID. So we're going to use this BPF get current PID TGID function to get the PID, and then we're going to do some bit manipulation to get the thread group ID. As a note, the kernel considers what you consider to be a PID in userland to be a thread group ID, and a PID in the kernel means something different. So we want the TGID here. We're going to get that, and then we're going to call this function, which is BPF printk, to say what PID we just saw. This is actually a macro. So this brings us to our first aside about compilers. The general view of a compiler you will use is just a box that you shove source code in one end and get a binary out the other. But in C-like languages, there's actually a first step where there is a preprocessor. This is where imports actually happen, but also macros. So this will create a kind of generated source code, which will then actually be compiled. So you can expand this, and you can see that this macro actually produces code that looks like this. We just allocate that string, and then we pass it into the real function, which is BPF trace printk, along with the size of the string. So that's just a helper macro, but this is what the code is actually calling. So our two functions that we actually care about are BPF get current PID TGID and BPF trace printk. And as I said, technically those imports are done in preprocessing too, but I haven't filled them out on the slide just because it would be too big. This helper function gives you kind of print-like stuff. So if you imagine print from most languages, print stuff to the console. You can't do that in eBPF because you don't have a console attached to print to, but you can put stuff into a kind of tracing debug file, which is what this is used for. You wouldn't want to use this in real eBPF code, but for debugging it's quite useful to get information out of an eBPF program. And then at the end of a function, we're just going to return 0. So all nice and simple. So let's compile it. We can do it with a command that looks something like this. We're going to use clang, which is a C and C++ compiler. We're going to tell it we're going to be targeting BPF here, so to get eBPF bytecode at the end of it. We're going to turn on warnings. We're going to pass O2 to get optimization. We're going to tell it we want an object file at the end of it, and we're not going to talk about why it's an object file and not an executable. We pass in a source file. We tell it the output file we want, which is just a .bpf.o, and that's just a convention. And then we're going to tell it where the includes are for our platform, which on the system I'm compiling this on is going to be under user include. As an aside, what the hell is clang? Well, it's a compiler front end for LLVM, which is what Wikipedia will hopefully tell you, which is rather useless unless you know what LLVM is. So what's LLVM? It's this is what Wikipedia says again, which is probably not all that useful. A better way to think about LLVM is that it's a set of technologies to build compilers. The core idea with LLVM is that instead of writing something that goes straight from a source code to a machine code, you instead have a series of front ends which take in the source code and a series of back ends that produce machine code. And then you have some common optimization steps that occur in the middle. This means that if you want to implement a new language, you can just write a new front end and then all of the back end will immediately give you multi-platform support. And if you want to add a new platform, you can just add a back end and then all languages will suddenly start working on it, in theory. Interestingly for us, there is an eBPF backend, which means that you can shove pretty much anything in LLVM in and get eBPF out the back. I don't actually know if someone's tried writing eBPF from Fortran. I don't suppose it would go very well, but I don't know. So this is more like what's actually going on. We're doing our preprocessor step, and then we're going for the LLVM kind of mid-step optimizers. There's an LLVM IR, which is the intermediate representation. And then finally, we're getting bytecode out the end, and then our object file. And there's also a thing about linkers, which we're also just not going to talk about here. As another note, those of you who are more familiar with eBPF will probably be wondering, what about SEC? Why haven't we declared our license? Why haven't we told the eBPF which function it needs to attach to? And normally when you write eBPF using a library, or especially libbpf or some other things like that, you would attach this information in the actual source code, but we didn't. So why? Well, these are actually macros which come from libbpf itself. And what these are doing is providing extra information and hints to the eBPF loader program to tell it where to put this stuff. It's not actually part of a compiled program in any meaningful sense of what's executed. The kernel doesn't understand this by itself, so we don't have it. Which is just what this is. We're going to do the heavy lifting ourselves. So, with that being said, let's take a look at what's been produced. What bytecode have we made? Well, we have this trace.bpf.o file. We can see that it is 792 bytes in my case, may depend on your platform. And if we take a look at it, we can see that it's a 64-bit, least significant bit relocatable eBPF file, is what file tells it it is. But we can take a bit of a closer look at it. So this is using a hex dump to get some information about the file. We can see that there are some strings in there. We can actually see our source is called from PID string, which is a good sign. We can see a few other things as well, but we can't really make much sense of the rest of it. More interestingly, we can use a program called readelf. So this file, pardon me, is, as we said before, an elf executable, which is an executable file format primarily used on Linux and on other platforms. Elf files have sections which have headers, and readelf will tell us what sections there are. And we can see in here that we have sections named .text and .ro data and symtab and things like this. The one that's interesting to us is text. That's where the actual program is. And we can tell it we want to see that. We want a hex dump, using readelf again, of the .text section. And that's going to give us this data out, which again includes our string, which is very useful. So as a complete aside, what actually is this bytecode other than the strings? What is the rest of this stuff? Well, let's talk about instruction encodings. eBPF has two of them. There's the basic one, which is 64 bits long, and then there's a wide one where you have a second 64 bits called an immediate value afterwards. And the instructions are encoded with an opcode, a source and destination registers, some offset, and a immediate value. So let's read through and try to decode one of his instructions. So we're going to take the first 64 bits from the text section, which is the actual compiled code, and we're going to take a look at it. So that's what it is. 85, all zeros, and then the second one is a 0 with an E, then all zeros. So what is this doing? Well, it's opcode 85, the source and destination registers, and the offset is 0, and we have an immediate value of 0E, and the rest zeros. So what's opcode 85? The 3 least significant bits of the opcode, because that opcode is 8 bits long, tell us what the instruction class is, and that 85 means that the binary representation of our opcode is this, which means that the 3 least significant bits are 101, which, if you come look up on that table, is a 64-bit jump operation. If you further read the eBPF specification, it will tell you kind of more information about how this code is interpreted. So we can see that the first 4 bits is some kind of jump code, and then there is also a 1-bit source, which tells us where it's going, which is either the 0 for immediate value, or if there's a 1 in there, we use a source register. And ours was 0, so that means we're using the immediate value. I'm not going to show you the code for those first 4 bits, but if you go and you look it up, this is a BPF call, which is call helper function by a BTF ID. And then we have our immediate value. As a little note, eBPF is little endian, which I'm not going to get into the details of. So the byte order is actually reversed. So that number is actually 14, not like 200 million. So what this actually translates to is call eBPF helper function number 14. Why number 14? What does that mean? Well, if you go look in like the kernel static information for what the helper function IDs are, we can see that helper function ID number 14 is get current PID TGID, which makes a lot of sense because that's the first thing that we were going to call in our source code anyway. So that sounds about right. The first thing we're doing is calling this function. As a side note, you don't have to do this manually. There is a program called LLVM objdump, which works in eBPF and can give you a load of information about what these things are, and we'll do this translation for you. I can see here that we can see there that the first line there is call 14. But if you're looking at this, you might wonder what the rest of this stuff is. In particular, what's all this about? Well, we need to talk about registers very briefly. eBPF has these general purpose registers. So R0 is a return from function calls, which means that the function call we do in call 14 will be put in R0, for example. Then we have some immediate ones, and then R10 is a read-only frame pointer to access the stack. And you can see here, we're doing a bunch of pointer arithmetic with R10. So we're pushing data onto the stack here. But what is this random data? Well, this is our string. This is our string broken up, and we're pushing it on backwards. So we are going to push these bits of information on in order to build our string up into, which we want to output, into the stack. So going back to something we talked about before, what about this BPF no global data? Well, now we can finally explain that. If you didn't have BPF no global data 1 at the top of your program, then when it compiles it, what LLVM will do is instead of pushing static information like strings into the text and pushing it onto the stack manually, it would instead encode it into a bit of the file, a bit of the produce object file called RO data, read-only data. And if you look in that, you'll be able to see our string. Again, this is compiled with that flag removed. And if you look at the text, it will tell you, you can see that we can't see our string in there anymore. There's significantly fewer instructions. And there's a little note saying there's relocations, but they've not been applied to this dump. That's a bit of a hint. So if we take a look at these instructions, we can see that all we're doing is the same call, and then we're not doing all the same stuff we were doing before. So what happened to our string? Well, if we look at the relocations, which is this -r, which is the .rel.text section, actually, it's going to tell us some information. It's going to tell us an offset, some info, and some symbol value and the symbol's name, and what kind of type it is, which in this case is just a 64-bit value. But what we can actually do is we can tell LV objdump to apply the relocation. And this has told us that in instruction 2, we should not be pulling nothing, but we should be pulling information that is contained in the RO data map. You can see this. This is back in that offset. The offset is in binary, so that's instruction number 2. So this offset is telling us that instruction number 2, the third instruction, needs to be modified. So this means that if you want to do eBPF with static values, like quote unquote properly, then the loader needs to do a bunch more work. What it needs to do is it needs to create an eBPF map for constants. Then for every relocation, it needs to find the data that's being referenced in the object file. It needs to load that data into the map from userland, modify the instruction that it references to load from that map instead, and then mark the map as immutable at the end of doing all the relocations. And we don't have time to talk about maps in any detail, so we won't go over that. But the reason I have that line in there is just because the loader, which we're going to go over in a minute, is so simple, it doesn't do any of this stuff. So in order to cut down on complexity, I didn't do it. But that explains what that's about, and a real loader would do this properly. Speaking of loading, let's actually go over how to do that. As another note, a library would make this like 2 lines. This is not going to be 2 lines. So we have a few things that we need to do in sequence to make this work. We need to load the bytecode into memory. We need to load it into the kernel from memory, and then we need to attach it to something, in our case a trace point. We're going to do everything in C just because it's a little bit easier to follow. But you can mostly do this in a language. There are libraries in Rust and Go and all sorts of stuff. All right, here's our loader code. So the first thing we're going to do is we're going to open our object file as read-only. We're going to get a file descriptor to it. As an aside, you might wonder what a file descriptor is. Pardon me. This will become important later, so I'm going to go over this now. The idea in Linux is that a process, when it refers to a file, has a file descriptor, which is just a number, which is how that process understands that file. When you open a file from a Linux process, what you're actually doing most of the time is getting a file descriptor to reference that file in future syscalls. Typically speaking, the first file you open will get a very low number because it's sequential, and things like std and stdout are also file descriptors. But we will get an FD to the object file. Then we're going to use a library. We're going to use one of the elf loader libraries. This isn't an eBPF specific library, it's just for elf, just to make it a little bit easier to pull out our compiled object code. We're going to tell it to do elf begin on the file. This library, by the way, this is just me talking about the library and how it's a generic library. No eBPF involved here necessarily. We're going to iterate through the sections. So we're going to we're going to get the file header to begin with, and that'll tell us how many sections there are. Then we can iterate over the sections. This code looks a little bit clunky, but don't worry, we'll go through it. First of all, we're going to allocate a pointer for the data for each section. Then we're going to loop over each section based on its number. We're going to get its section information. We're going to get its section header. And then we're going to get its section name. And, before we go ahead, you might be wondering what this char star stuff is about. For those of you less familiar with C, C doesn't really know what a string is. It knows what a character is, or rather it thinks a character is a single byte. So the way C understands whether or not a string has ended is typically they will either just have a null byte at the end, a null terminated string, or they'll have a specific length of a string that they will read, or they'll just segfault. If you want to talk about Unicode and how this works for Unicode, send me a message after this or send me an email or something, because that's a whole different thing. Getting back to this, we now have a string, that char pointer for the section name, and we're going to compare it to .text. In this case, we're just giving the length of the string. And if it is indeed a text section, then we're going to get the data. So what this block of code on the screen is actually doing is it's looping through the sections until it finds the text section, which remember has the compiled bytecode. And then it's getting a reference to it and put it in this elf data pointer. We're going to do some error handling. If we didn't find the data, we're going to error out. And then that's it. We've read that data into memory, but it's not in the kernel yet. So how do we do that? Well, we'll use the BPF syscall. You can get information in this using the manual page, so like man2bpf will tell you about this. This is syscall kind of does everything to do with eBPF. So we need to give it a command. The way it works is you give this a command, and then you give it some attributes and the size of those attributes. And the attributes vary depending on the command. In our case, our command is bpf prog load, which is verify and load an eBPF program, and we get a file descriptor back. I told you those would be important. We can also see what information it expects us to give. See, there's quite a lot of stuff here, and we'll go over this in a bit more detail in a minute. So here's a load of code. First of all, because this syscall also does verification, we can get errors out, but the syscall can only return an integer. So we need a way of getting from the kernel more detailed diagnostic information about why a program failed verification if it fails. The way we do this is we're going to allocate some memory in userland, this 10 kilobytes I've got here, for log buff, and then we're going to pass a pointer to that in, and then tell it what log level we want. And then after the program is run, it will put a string in here to give us any diagnostic information it needed to output. We're going to specify the license. Licensing is an interesting one with eBPF. There are certain internal helper functions which you can't call unless your code is GPL licensed. Dual licensing is fine. I believe printk is one of the GPL licensed ones, so we need to be GPL compliant. So we're going to declare our license to be dual BSD GPL. Then we're going to get a pointer to the instructions, and we're going to give it in, and we're going to tell it how many instructions there are. And remember, our data size there is in bytes, but each instruction is more than 1 byte. So we need to tell it how many instructions there are, not how many bytes. So we have to do that division. As a side, what is this instruction? Well, this is just a struct which provides useful referencing in C into the instruction. You can see it's the same layout as before. It's the code, then 4 bits each for the registers, then the offset, and then the immediate value. Which is the same thing here. So if you compare it to that, you can see how we can pull information out. You can see here's the first 2 instructions in bytecode. And you can see how we could index into them using a char pointer, which is just 2 individual bytes, and then also index into it using instructions. And the size of the pointer is also important here. So we need to make sure we pass in a pointer to an instruction and not a pointer to a byte. So then we just calculate the size, as I said, and then we're going to set our prog type as well, which is BPF prog type trace point. And that'll come up again in a minute because we're attaching to a trace point. Different programs attach to different things. Finally, we're actually going to call our syscall. So we're going to do the BPF syscall directly. We're going to tell it BPF prog load. Then we're going to pass in our attributes. And then we're going to do some error handling if we don't get a BPF file descriptor out the back of it. So what does this actually do? Well, talked about logging and okay. Yeah, we loaded into kernel, but what does it actually do? Well, we can take a look in the kernel and we can see because the kernel is open source. So if you follow the way down through kernel source code, you can get some idea of what's occurring. I'm not going to be showing all the kernel code here, only the relevant bits, because there's quite a lot of it, and some of it really isn't relevant for our use case. So follow me along here. So kernel BPF syscall at C is where the syscall is defined as this function. This returns an internal function called __ sysbpf. And by the way, this is all on a particular version. So I'm doing this on Debian 12 on the 6.10 kernel. So this might be different in other kernel versions or in different distributions which have patches for kernels. I don't think this code has changed all that much recently, but if you look yourself, it might be different. So what do? Well, one of the first things we do is permissions checking. We check to make sure that you have the Linux capability to do eBPF loading. If you don't, then it'll error out. This is why you normally need to be root to load eBPF programs or have capabilities granted to you to do it. We're going to do some edge case checking on attr. Then we're going to copy the attr that you gave in, that attributes map, into kernel memory. This means that it can't be mutated by the user while this is happening. We're also, now that we've got the attrs over into kernel memory, going to ask the security subsystem if a call is allowed. So this is where AppArmor or SE Linux or something like that would come into play to allow or deny eBPF calls. Then we just have a massive switch statement, which has one pair operation type. Further down, there's BPF progload, which is for us, which calls a function called BPF progload. In there's a lot of stuff I've omitted, but here's where we do the license checking, for example. We'll go and we'll check to see whether our license is GPL compatible, and if it is, based on some string comparisons, we'll set is GPL. We're going to allocate kernel memory for the bytecode, and then we're going to ask security again, just for good measure. Then we're going to copy it over from the user memory into kernel memory. So this means, again, the eBPF bytecode can't be mutated after the fact. We're going to specify that it hasn't happened yet, and then we're going to run the verifier. I really don't have time to get into how the verifier works, but in essence, this just checks that it's not going to do anything particularly untoward when running under kernel space. It is a whole set of topics all by itself. Then we get into the actual compilation. So this is what the just-in-time stuff is about. So the whole idea with eBPF is that eBPF bytecode is portable. You can run it on any machine. But in order to provide adequate performance, it doesn't run an interpreter. The kernel does not run an interpreter for eBPF bytecode on the fly. It compiles it itself, again, down to the actual supported architecture microcode of the running platform. And it does this using this BPF prog select runtime. This happens after verification. This is incredibly platform specific, but I can talk about it a little bit for the platform I was running this on, which is x86-64. Roughly speaking, you can see how this is going to work. We have a switch statement on eBPF instruction opcodes, and then we're going to output x86-64 opcodes. One way we can do, there are a bunch of ways of viewing the compiled BPF. There are some better ways of doing it than this. This was just a quick and dirty way I did. Is we can set a debug flag to globally produce the just-in-time compiled version to the dmessage log. So we can do that, and then when we run the compiler, we get this code out. I'm not an expert on x86-64 bytecode, but you can see it looks roughly correct. If we use BPF JIT-disam, which is another utility to kind of get some information about this compiled bytecode, we can see that we're doing some syscalls. We're moving some stuff into the stack in order to load our string. Not syscalls. We're calling our helper function BPF get current PID TGID. And then at the end of a function, we're doing BPF trace print K. So you can see it's pretty similar to what we expected before. And you can also use BPF tool to make this a bit easier if you're actually doing this yourself rather than this slightly hacky debug workaround way. Right. So we have some compiled code, and it's even in the kernel, but it doesn't do anything by itself. We need to attach it to something to produce something useful. So that's where the tracepoint attachment comes in. The BPF syscall manual page tells us that this depends on the type, so it will depend on the type. For us, for a trace point, we can do it this way. Firstly, we need to get a file descriptor to this file under syskernel. We're worried about the sysenter xcave trace point. That's what we're going to try to attach this to. And we want to get its ID. So we're going to open this ID file by getting a file descriptor. We're going to read it by running the read syscall. Then we're going to close it. And that gives us the string representation of the ID of the trace point, which we then going to convert using A to Y. And then we have the ID of a trace point. Then we can use another syscall called perf event open to get a reference to that trace point using its ID, which we just read from that file. So we're going to tell it we want a trace point. We're going to give it the trace point ID. And this is going to give us another file descriptor. And that is what perf event open does, by the way. So this starts performance profiling in a way. perf is like an entire other subsystem, which I don't have time to talk about in the Linux kernel. And yeah, what all this is saying is it gives us a file descriptor, which you can then use to do other things, such as with IOCTL and PRCTL. And IOCTL is the one we need. So we're going to give it our tracepoint ID. We're going to tell it that we want to associate a BPF program with this perf event. And we're going to give it a file descriptor of our BPF program that we got out of BPF syscall back when we loaded the program. What does attachment do, you might ask? Well, again, this is very specific to trace points because attachment is different depending on the different mechanisms. But we can get a general idea by, again, looking at the kernel code. We can see that under the code for perf event IOC set BPF, we're going to call a bunch of helper functions. We're going to call down into perf event set BPF prog. That is going to call down into perf event set attach BPF prog. It keeps going. The short version is that what this will ultimately do is attach a reference to the eBPF program to a list of programs on the trace point. And if a trace point is open, there is a highly platform-specific way of creating a syscall which will be modified. So there's no generic explanation. It depends on the platform. This ultimately will invoke trace sysenter, which eventually will call the tracing subsystem, which eventually will call the eBPF code. So there's a lot of indirection going on here, which is a bit hard to follow. But the short version is that opening a trace point changes the way the syscall works, and it will check for eBPF programs that are attached in the list. So, what have we done? We've attached it to our trace point and told it we want it to run every time this syscall is run. So, finally, we can compile everything using our compilation. We can compile the eBPF code. We can compile our loader code. Then we can run it, and we need to run it as sudo. That's going to give us a bunch of output. And then in another terminal, we can get our tracing pipe, which is where printk outputs to, and we can see that something made a syscall. Thank you. That was a lot of data in a very short period of time. I have a whole bunch of further reading and some special thanks to people who helped me with this presentation. If you have any questions, please do be in touch. Thank you.